All right, let's take a look at section 6.1, which is about exponential growth and decay functions. Um, so hopefully right here, we're looking at something a little bit new, not completely, um, but let's take a look at what some of these functions look like to start off with. We have right here our exponential function, and that happens to be y is equal to a times b to the x power. So you got to make sure you understand what this function looks like and that it is an exponential function. But down below it, we have this exponential growth function. And what I want you to pay close attention to is this b that we have in the exponential function, our generic function right there, and how there is no b in the exponential growth equation. It's y is equal to a times parentheses 1 plus r to the t power. Well, that 1 plus r happens to be your b value. So taking a look at this right here, we should now realize that this 1 plus r right there is the same as your b. And then it is raised to the t power. We talk about exponential growth, and you're saying, well, where does that t come from? Well, it replaces the x, but t represents time. R will represent the rate. And those are the main differences right here between the growth function as opposed to just the exponential function itself. If we drop down just a little bit right here, you'll see that we have the exponential decay function. So let's take a look at that next. And right there, it's y is equal to a times 1 minus r. And so this 1 minus r right here represents that b. And the reason why this is decay, and hopefully you see the main difference, is that we have 1 minus r right here as opposed to 1 plus r with the growth. All right, so those are your two functions that we're going to be primarily looking at right here in this section. Let's go up right here. We talk about the asymptote. And the asymptote is a vertical line that the function does not cross. And we've talked about the asymptotes already. And let's take a look right here. Let me draw a function. And it will look something like this. So that function right there that I just put in red, that is your exponential, we'll just say it's an exponential growth function. Well, it is growth because it's going upwards from left to right. Now, what you'll notice right here is that we do have an asymptote. And where is it? The asymptote, I tried to make it right here at the x-axis. And I'll go ahead and put a dotted line there, or a dashed line. And that asymptote would be, in this instance, a horizontal asymptote. And what I need you to understand here is that in this exponential growth function, when you're going towards negative infinity, all right, when x is going towards negative infinity, that red part right here, this portion right here, it looks like it's going to hit the x-axis, but it actually does not. It gets very, very close, but it will never cross that x-axis, or x is equal to 0. Mathematically, you'll see if you were to plug numbers into a table, that it'll constantly get smaller and smaller and smaller. And it looks like it'll get very, very close. It'll be like 0.000000000, keep going on, 0.12578. It's going to be very, very small, but it will never, ever cross. And that is one of the key things to understanding the asymptote and our exponential functions. All right. Let's go ahead and move along. So what I showed you right there was pretty much a parent function for exponential growth. And if we take a look at what we in this core concept, it talks about there is no a value in this parent function. But if you think about the a value, it's in front of the b, and when it comes to our functions, our transformations, it will be your, vertical stretch, vertical shrink. So right here it says in the function f of x is equal to b to the x power, where b is greater than 1. This is the parent function of the family of the exponential growth functions with a base of b. Now, in the parent function, what you will notice is that right here, the function will always intersect at 0, 1. Okay, that's in the parent function. And look at one of the points. It happens to be right here at 1, comma, b. So there's another point. That shows you the significance of this b value. Okay, because the b value is actually going to be one of the points that you plot in your function. Okay, so it says right here the graph rises from left to right, passing through points 0, comma 1 and 1, comma b. The x-axis right here on the left-hand side, it says the x-axis of the graph. An asymptote is the line that a graph approaches more and more closely. But once again, I say, hey, it's not going to intersect. The domain of this, okay, we think about what is our domain, what is our range. Remember, domain is your x. So our function is going to go infinitely towards negative infinity. It will actually go positive infinity as well for x, but it'll also go upwards at the same time. So domain right here, it tells us that it is all real numbers. Well, what's our range? Well, remember, the range is your values of y, and since it's not going to ever cross the x-intercept, our range is y is greater than 0. Not equal to 0, because if it's equal to 0, then that's not the x-axis is not the asymptote. So that's right there are some of the key highlights to our function. So we've looked at primarily growth so far, exponential growth. Well, how about our exponential decay? Well, in our exponential decay, that's when my b value happens to be less than 1 and greater than 0. And so in the writings right there, it says the function f of x is equal to b to the x power, where b is less than 1 and greater than 0, is the parent function for the family of exponential decay. And so remember, in exponential decay, going from left to right, it will be going downwards. And so, where do some of these points, how are they significant? Well, first off, I know it's decay because my b term is going to be less than 1. Okay, 0.75, 0.5. They can also give it to you as a fraction, 1 over 12, 1 over 4, etc. It's going to be a small number. So that tells me automatically it's going downwards. And that b value right here happens to be also one of your points at 1, comma b. You can see right here in the example, hey, there's one point right there, and another one is at 0, 1. Okay, so those are some of your key points right here. When it comes to actually graphing these points, you are going to need a calculator to be able to graph them, because in order for you to get some of these points and numbers, you're going to get some funny numbers, irrational numbers possibly, and so you're going to need to make sure you have your scientific calculator there. What I care about most, the biggest thing is, all right, do you understand the transformations of things? If you were to, what does the a value do? The changes in the b value, whether it's exponential growth or decay, knowing where does it cross along the y-axis. Those are things that you're going to have to figure out. Right here, domain, once again, is all real numbers because it keeps on going outwards, both up and down. After that, the range, remember, at the x-axis right here, you've got yourself your asymptote. And that function does not cross the x-axis, or it does not cross y is equal to 0. So therefore, the range is y is greater than or equal to 0 in this problem. Let's go down and check out next compound interest. With compound interest right here, guess what? I said you got to memorize something. Well, you've got to memorize the equation, okay? There's no way around this. Sometimes they give you the compound interest equation. I am not, so you guys need to make sure you know the compound interest. Consider an interest principal. Okay, we use the letter P for principal, and then it's deposited in an account that pays interest at an annual rate of R, expressed as a decimal. So right here it says compounded n times per year. The amounts A in the account after T years is given by this equation, once again, that I'm asking you to memorize. Well, what is compound interest? Hopefully, maybe you've learned a little something about money. But with compound interest, it's something that you're going to want to have when you're maybe investing money into a bank or into some sort of special account, is that, let's say you're going to invest some money. We start in January. Hey, it's a new year, right? And in January, you've got $100. And you're going to invest into an account that gives you 1%. Okay, so 1% of 100 would end up being $1. And so let's say it's compounded monthly. In February, that means you're going to be getting $101. Okay, that's how much your bank account will actually have. Now, if it's not compounded, the interest is not being compounded, what happens the next month is that you're going to be getting interest on $100, not on $101. Well, I would rather get interest on $101 because then your interest will end up being a little bit more, right? Because if not, what ends up happening is that you get interest on $100 again, meaning you're going to get another $1. And then in the end of February, or when you go into March, your bank account will be at $102. But let's say right here, instead, you went ahead and you're getting, what is it? You're getting compound interest. Hey, you're getting interest on $101. Therefore, your interest for the month of February will now be $1.01. Now, it seems minuscule for now, but over time, at least, hey, you're making another penny, and your bank account is going to be growing at a much more rapid rate than if it was just, or at least it's going to be growing better than just having regular simple interest. Okay, so those are the differences right there. So we have right here, you got to, once again, I put down principal is P, that's your starting amount. R is your rate, and that's expressed as a decimal. N is the time compounded per year. How many times? Is it quarterly? 4 times. If it's biannually, 2 times. If it's daily, hey, more power to you. So it's going to be maybe compounded 365 days or times. Okay, and then the time, how long? 1 year, 2 years, 3 years, 10 years, 20 years. That right there would be considered your time. All right, when we take a look at compound interest. So let's go ahead and take a look at some of these functions and figure out what does all of this mean. So right here on number 1, it says tell whether the function represents exponential growth or decay. Remember, it is your b value that will help us understand that. So what is the b value? It's that 1 over 12. Is that less than 1 or greater than 1? I'm pretty sure 1 over 12 is less than 1. So what that tells me is that this function for number 1, 1 over 12 to the x power, happens to be decay. All right, so we can go ahead and safely say because of that, we've got decay. They ask you to graph the function. Remember, for right here, my parent function says that one of the things is that it goes through at 0, 1. Well, the best thing you're going to do for these problems here is create a table. Okay, so what I would do is go ahead and say, like, if we were to do this all by hand, we would create a table. And I'll go through that process right here for the first time around. And so we can go ahead and put numbers like, let's just say 0, 1, 2, -1, -2. And you start plugging things into the equation. 1/12 right here. We'll raise that to the 0 power. And remember, there is a rule that we've had for that. And when our base is raised to the 0 power, it happens to equal 1. Okay, so let's repeat. We got 1/12 to the first power. So 1, comma, and then that'll be 1 over 12. And you see how, remember, one of the points happened to be at 1, comma, b. And that's right there with 1 over 12, 1, comma, b. We can go ahead and repeat this. We got 1/12, and then we'll raise that to the second power. And then we have a nice small number. And it's going to be 0.00694, and it keeps repeating itself. All right, so how about this? I went ahead and showed you how we do it by hand. Let's go ahead and take a look right here over here at Desmos. All right, so over here on Desmos, went ahead and hey, look, we've got some of these numbers already figured out. And so for -1, we have when x is -1, y is 12. When x is -2, y is at 144. Okay, so we start plotting the points, and you're going to want to go ahead and graph this on your student journal or in your notes. So go ahead and please make sure you add this here. Let's go ahead and see what it looks like. It's supposed to be going down from left to right. Does that happen? It sure does. Let's take a look at it right here. And it went down from left to right. Some of our key points. The first one right here is at 0, 1. Okay, you can see that first point there. Remember, another point is at 1, comma, b, which is 1 over 12. That will be this right here at 1, comma, 0.083. And right there is your function. Just plug in a few points, and bada boom, bada bing, you know how to graph this now. Okay? So next up, let's go ahead and take a look at number 2. So don't forget to make sure you have the graphs in your notes. I'll be looking for them later on. So let's take a look next at number 2. Right here, I take a look at my b value, and I've got 1.5. That right there is greater than 1. So what that tells me is that we have ourselves an exponential growth. So from left to right, it is going to go upwards from left to right here. When you plug in points, you can plug in -2, -1, 0, 1, and 2. Okay, so go ahead and make sure you plug those things in, and then you can go ahead and put it all together. Okay, so we'll go ahead and let's see. Hopefully it shows up on your screen. We've got ourselves that 1.5, and then we've got ourselves exponential growth. Okay, so I'm plugging points in, and let's go ahead from our calculator, save us some time. Let's go ahead and we'll take a look at Desmos right here. And we have ourselves at 1.5 raised to the x power. Those are your points. You can see it all on the screen. So now, since those are your points, let's see what it looks like. Remember, it's supposed to be going from left to right upwards, and lo and behold, there you go. Now, one of the points right here goes through 0, 1. There you have at 0, 1 being highlighted right now. And then at your other point is at 1, comma B, B being 1.5. And there you go. Hopefully it highlights for you. There you go, at 1, comma 1.5. And it is going left to right. We have, don't forget, on the towards negative infinity for x, over here, it is going very close to the x-axis, but it actually doesn't cross. And if you were to zoom in, you'd see how it gets very close. It almost looks like it touches, but if you zoom in even further using Desmos, you'll see it doesn't touch. All right, it does not cross, it does not intersect. You could look at the table and see how the numbers are getting smaller. Right, at negative 1, you're at 0.6. At negative 2, you're at 0.4. At negative 3, you'll be at who knows what, 0.2. Okay, so it's going to constantly get slower, get close to 0, but once again, it does not intersect. All right, so we have that right there. All right, so let's take a look at number 5 next, which is about the number of bacteria in thousands. In a culture can be approximated by the model of y is equal to 100 times 1.99 raised to the t power, where t is the number of hours the culture is incubated. So part A says, tell whether the model represents an exponential growth or decay. Remember, we have our equation, y is equal to a times b to the x power, or once again, let's take a look. It was y for exponential growth was a times 1, either plus r or minus r. So I'll go ahead and put plus r and then raise to the t power for time. Now, let's think. How do I get 1.99? What do I have to do with 1? Hopefully we realize that 1.99 is greater than 1. Therefore, I have to add that 0.99 for us to get that 1.99. So let me go ahead right here. I'm going to change this to 1 plus 0.99, and then we have our equation. For a, we can go ahead and keep that as 100, and there's our function. Well, if you haven't figured it out now by what I've been saying, this model right here represents exponential growth. We go to part B. It says identify the hourly percent increase or decrease in the number of bacteria. Well, that percent, okay, that right there is key. Remember, it is the rate that we're going to be using to figure out that percentage or get that percentage. The rate right here, once again, that is this 1 or this 0.99. So we can go ahead and put this as 0.99. But 0.99 is a decimal. We have to change this to a percentage. So hopefully, remember, maybe in elementary school or middle school, I guess, which way does the decimal point go? From decimal to percent, the decimal point goes to the right. From percent to decimal, it goes to the left. So if we take a look and put all that stuff together right here, I have a percent. I need to change it to a decimal. Let's go ahead. We need to move our decimal point 2 spots to the right. And this will now yield into 99%. That's quite a bit of increase, 99% right there. So that is the increase in our problem. So next up says, estimate when the number of bacteria will be 1 million. Now there's a key thing to this problem. Up in the very beginning, it says the number of bacteria Y is in thousands. Now, you know, they got to always throw a loop at you, right? Throw a little some extra little curveball. And so what do I do with this number? Well, the number of Y in bacteria is in thousands in a culture. What we're going to have to do is, let's take that 1 million right here, and let's go ahead and convert that to our bacteria in thousands. And I'm going to take this 1 million and divide that by 1,000. And unfortunately, if you don't do this part correctly, you're going to be in a whole world of hurt. You're like, man, I can't get this answer. So we're going to look at how the number of bacteria will be actually 1,000. So let's go ahead. This 1,000 will represent Y. And so let's take 1,000 and set that equal to 100. And then we got to the 1.99 to the t power. And let's go ahead and get t by itself. So first things first, let's go ahead and divide both sides by 100. And so from there, now I end up with 10. Okay, so I'll go ahead and rewrite our equation right here and put it as, let's go ahead and say 10 is equal to 1.99 raised to the t power. What do I do next? How could I get t when t is an exponent? Well, you can't. We didn't learn that. So what we're going to have to do now is do your favorite of guess and check. And the funny thing is, when I ask you to guess and check, you don't know how to do it, or you don't do it. And when you're supposed to actually solve a problem, you try guessing and checking. What gives? I don't know. So right here, how am I guessing and checking? You take your 1.99 and you start raising it to different numbers. Obviously, 1.99 to the first power is not going to get us 10. And so this is not an exact science right here, unless you're using like a special calculator. So what we're going to end up doing right here is just start plugging numbers. All right, let's raise that to the second power and see what happens. I end up with a 3.9601. So that's not good. Let's take 1.99 and raise that to the third power. I get 0.788. We need to get it to equal 10. Well, how about 1.99 to the fourth power? At that point, I'm at 15.68, right? It's getting a little too high. Maybe you can see that right there, maybe not. So what do I do now? Well, 4 is too much, 3 is too little. How about 1.99? We'll raise that to the, let's put 3.5 power, okay? And that's at about, what we have 11.11, a little too much. So how about 1.99, raise that to the 3.2 power? I'm at 9.04. We're getting a little bit closer. Maybe 1.99, raise that to the 3.3 power. And I'm getting 9.6875. So you can see how guessing and checking is being worked right now, hopefully. And I'm going to go ahead, 1.99, we raise that to the like say 3.4 power. and I'm at 10.37. So a little too much. So maybe 1.99 raised to the 3.35 power. Oh, and I'm at about 10.02. That looks like it's pretty good, right? So I guess and check right here and realize that if I put 1.99 and we raise that to the 3.35 power, that will get me approximately 10.02. And so this is like an estimate. And so my answer right here would be 3.35. Guessing and checking. Okay. Unfortunately, right here, there is no way for you to actually solve the problem out. So we do a little guess and check and just start plugging in numbers until you can get to our value that we need here. All right. Last up, we got right here. Let's take a look at some compound interests. I always find this stuff very interesting because it's, you're dealing with money. And I think we're at the point, and you're at the point of your lives where, money is a good thing, right? You always want to buy stuff. So hopefully we can try to maximize our dollar. So how do we put all this together? Okay, first off, we've got an equation. Let's go ahead and write down what the equation is. A is equal to P, which is once again your principal. And then you got yourself parentheses 1 plus. And then we have R, which is your rate, over N. And then raised to the NT power. Now, one of the key things right here when it comes to this question is, and these types of problems, is anytime you see interest right here, you've got to make sure you take the interest and turn it into a decimal. Okay, so take that, rewrite to a decimal. If not, your numbers are going to be all wrong. All right, unfortunately. So we're going to go ahead and let me rewrite this to change that to 0.0225. And you're saying, well, how did I get that number? Remember, right up here in this last problem, I showed you the decimal 2%, percent to decimal business right there. Well, there you go. Decimal to percent, two decimal points to the right, percent to decimal, 2 decimal points to the left. And that's how I get the numbers. All right. Other things that you should know. Quarterly. If you split up something into quarters, you're split up into fourths. So that means that we have interest happening 4 times. We got principal is 1,250. So the amount A in the account, that will be equal to our principal. Let's start putting things together. 1,250. You got 1 plus the rate. Let's plug in at 0.0225. We will divide that by n. Well, how many times? In the problem right here, it says the time is going to be 5 years. So I went ahead and highlighted that right now. We're going to go ahead and plug in 5 right here for n. And then we have the number of raised to the number of times to the t power. Oh, sorry. Time is going to be 5. The number of times we have is our quarterly. So let me go back right there. Let me go ahead and erase that. And next up, we have the number of times. It's quarterly, so it's 4 right here. Raise that to the 4. And then how many times? 5 times. Because that's what it says in the problem. So it's a matter of plugging things into the right spot and then getting your answer. Okay, so if you go ahead and use your calculator correctly. Make sure you practice it, because I see a lot of students mess up because they're not practicing plugging things into the calculator. You should end up with $1,398.40 right there, and that would be the amount of your account would be when you start off with $1,250. Your interest rate is 2.25% after 5 years. Okay, and being compounded quarterly. All right, let's try one last one with number 7. And so we have right here this 1.25%. We're going to go ahead and change that to a percentage, or sorry, a decimal. So 0.0125. We have is compounded daily. So that right there should tell us, hey, compounded daily, 365 days in a year. I'll just say we're not dealing with a leap year, right? Or anything like that. So we got 365. We start off with the same amount, right? It's still 1,250. We got 1 plus R, which is 0.0125. Since it's compounded daily, we'll put that over 365. And then we'll raise that to the n once again. So that'll be 365 right here. And then times 5, because it's after a 5-year time span. We'll go ahead and put all that together. You get yourself this lovely number of $1,000. We got $330.62. So you could see the difference in your interest can make a big difference. Okay, the rate, the amount of times you get interest, all those things are very big factors in you getting your answer, or getting your figuring out how much money you're going to make in interest on these problems. All right, so this right here we have now is section 6.1. If you have any questions, make sure you leave a comment or ask me during class. All right, and once again, the answer is taking a little bit of time showing up, but it is $1,330.62. And that right there is your answer to number 7.